All right. 6.4. Today's lesson is called the central limit theory. Informally, the way we can think about this, if n is big enough, meaning the samples that I take, the distribution of those sample means will be normal regardless. So the distribution will form that little bell shape of the sample means. All right, we are going to use, number one, the central limit theorem to find the sample means. And then we're going to distinguish between the individual mean and the sample means. So kind of the difference between 6.2 and 6.4. All right, here is the central limit theory. It's a little bit unnerving in that I don't know what the main purpose of this, because it doesn't seem to shed light, except for the mean, which may or may not be useful. But anyways, here's what the limit says. If our sample sizes are more than 30, then regardless of the distribution of that population, the sample distributions of the mean will be normal. All right, so the mean will equal the population's mean, and the standard deviation will be equal to the standard deviation divided by the square root of the number of sample items that I'm having. So here's an example involving 1,352 earthquakes. Okay. Remember that earthquakes occur somewhere in our mantle, right? The earth that we walk on, you and me. And they're sometimes below the earth. And so this data set here shows us earthquake depths of these 1,392 earthquakes, not 52. And we can see that this is not, in fact, if anything, there is a double mode going on. It's bimodal, so to speak. So it's not distributed. In fact, we even see a skewing to the right. But if we look at the sample means, all the possible sample means of this data set, meaning if you take little subsets, right, of different sizes, and this one specifically is of 50 earthquakes, then you get a normal looking distribution, which ends up being the mean. Whatever we get the mean of this will be the mean of the actual original set. All right. So observation number one. The data set is not distributed normally. Okay. Observation two. And yet the sample set in that n is greater than 30. They are normally distributed. So again, when I say that this doesn't seem useful to me, what I'm saying is that, if we know this, it doesn't seem to tell us too much about this other than the mean. Yes? So I'm curious as to how this plays out in the future. All right, notation. Here we go. Mu with x bar. This means the mean of the samples. And the same thing then with sigma x bar. This means the standard deviation of the samples. Things to keep in mind. We're going to assume that we have a population that has a given mean and a standard deviation, and they will give these to you. You don't typically need to figure those out. Then, second, we are doing simple random samples, all of the same size. Okay, key thing there. If that's the case, then these two facts are going to be true. So looking at our cases, if n is 1, we use 6.2. Yes? If n is between 1 and 30, we have a couple options. If they're normally distributed, then we can use the central limit theorem. If they're not normally distributed, then we have to wait to chapter 7 and 13. to figure out what to do. So if n is greater than 30, though, doesn't matter if there's distributed nicely or not, we can use the central limit theorem. So elevators is our first example. You've all been in one, hopefully. They've got signs as you board that kind of are unnerving. They say something about the maximum capacity. So 4,000 pounds, 27 passengers. First of all, this implies that the average weight that they're expecting people on this is 148 pounds. Assume that our population, which is Americans, is then 1,189 pounds per person with a standard deviation of 39. All right? So clearly our mean is greater than what they're expecting the mean to be. So two questions. Number one, find the probability that one passenger is over 148. And then find the probability that 27 passengers have an average, a mean weight greater than 148. So for part one, since n equals 1, we just use the concepts from 6.2. That is, we think about our standard deviation graph, we think about the mean and where we are, and we can see that this is a lot, so we find the z-score as we normally did, yeah? And then we either go to table or technology. I think with the table we get 0.8531, and with technology we get 0.8534. Negligible difference, so we can say that, for example, with some sort of confidence that approximately 85.3% of the population is, that the probability of one adult being over 148 pounds, okay? So again, that's just one of the. Now let's look at the second part of that problem, where we have the probability that all 27 passengers. First thing we notice here is that n is less than 30, right? Because we have 27. Fortunately, though, the weights of Americans are normally distributed. Therefore, even though we are under 30, we can still use this theorem. Okay, so we take our mu, set it equal to the given mu. Then we take our sigma of the different sample sizes, and we take our standard deviation divided by the square root of the number of items, and that gives us our new sigma for the sample sizes, which you can see is quite different than the original 39. All right, so a note here about this. When I now draw the graph, even though 189 has not changed, yes, notice the height of my curve has. And that's because the distance between 189 and one standard deviation is now just 7.5, where it used to be 39. Yes, so our graph is taller. And what that means is that the area inside here, the area inside here is going to be larger than what we previously had. All right, next I get my z-score. So 148 minus 189 divided by 7.506. Again, rounding that off, we get negative 5.46. So going to technology with this z-score, which is well below negative 3, right? It gives us something nearly all the population. Yeah, this is as close or as far away as 0 plus as you can be. And using the table, they just say if anything's smaller than negative 3, then use that value there. Okay? So we are certain that we will have any 27 Americans be over the mean of 148. Okay, how certain? We are super certain. And thus this sign needs to change, or somebody's going to get their themselves sued in court if an accident should happen. All right. Finally, there is a rare event rule for inferential stats. If the probability of an event is very small and the observed event is significantly small or large, meaning you're on those tails, right? Either you're less than 0.5 or greater than 0.5, then we can conclude the assumption is probably incorrect. All right, and that was kind of what we did on that last one. That assumption that this elevator can carry that is poor. All right, so here's an example from life. 98.6 is our average body temperature, and our standard deviation is 0.62. That is, as you look at normal people, we all have different body temperatures, but it's pretty close, you know, within 1 degree, 1.5 degrees roughly. Most of us would be in that range. So in a sample of 106, the mean body temperature that they found was 98.2. Find the probability that the temperature being less than 98.2 in this sample of 106, right? So what is the probability that this sample of 106 is less than 98.2? Or sorry, it was 98.2. First of all, as we notice, n is greater than 30, so bam, straight to the central limit theorem. Set mu equal to mu. Calculate our standard deviation. It's quite small, 0.062. Now find our z-score. Again, negative 6.64. Yikes. That is really small. So let's just grab that value from the table. If you're below negative 3, then you're 0.0001 from, again, this is from the table. So since it's so slow, we conclude one of two things. Number one, assuming the data is valid and 98.6 is the mean, then this was a rare instance. Okay, there is that possibility, but that possibility is really slim. You don't want to bet on that. So the other possibility is that either the data was collected incorrectly or 98.6 is not the mean of body temperatures, which turns out that that latter is the true one. Our mean temperature is not 98.6. I don't know what it is, but well, there you go. That is the central limit